So I will start the talk by talking about the Ricci curvature in manifolds before introducing a discrete notion of curvature in graphs called the Ollivier Ricci curvature. Then I will talk about an algorithm that uses this value of the curvature called the Ollivier Ricci flow, and I will mention one of its applications to community detection problems. And then I will focus on the main focus of my dissertation, which was the convergence, or in this case, the non-convergence of this Ollivier Ricci flow algorithm. And finally, I will just talk about some interesting points that we found along this project and future work that we could do. So there's a lot of different notions of curvature that can be defined in manifolds, but they all seek to capture the deviation of an object from being flat. So my dissertation focused on one of those curvatures that is called the Ricci curvature, and this one can be characterized in the following way. So given a manifold M of dimension n, we can take 2 points close to each other, x and y, and calculate the distance between them along a geodesic gamma. So then we can take a vector v in the tangent space of x and parallel transport it along gamma to a vector v prime in the tangent space of y. We then project x along v back to the manifold again to obtain x prime, and we do the same with y to obtain y prime. And we recalculate the distance between the points. So notice that we can do this for every possible direction of v and v prime, and then we get these small geodesic balls around x and y, and we have a well-known formula that relates the average distance between x prime and y prime with the distance between the centers of the balls and the Ricci curvature at that point. So from this formula, we can infer that when the curvature is positive, the average distance between respective points on small balls is smaller than the distance between its centers. So this will happen in surfaces like the sphere, for example. And then when Ricci curvature is negative, we'll have that the average distance between these respective points in these balls is larger than the distance between its centers. And this will happen in the hyperbolic space, for example, as well. So this is an intrinsic notion of curvature, which means that it does not depend on the space that is embedded in. So we would like to define a similar notion, but in the context of graphs. So of course, as graphs don't have a differential structure, we have to use different techniques. And in this case, the Ollivier Ricci curvature is an edge-based curvature that can be formulated in terms of an optimal transfer problem. So what we will do to define the curvature of an edge that joins two nodes x and y is to define a mass distribution around node x and a mass distribution around node y, and find the best way to transport one distribution to the other. So the mass distribution around a node x can be defined in the following way. So we put alpha mass at x and we equidistribute the rest of the mass among the neighbors. So this mass distribution can also be seen as the probability distribution. So these masses have to add up to 1. And alpha is a parameter that's called the idleness, as it can be seen like the probability of a random walker to not move. We then need to define these transfer plans that move the mass distribution around x or mass distribution around y. So these plans need to satisfy some conditions. And for instance, the first one, it ensures that all the mass that we move from a node k in the neighborhood of x to all the nodes in the neighborhood of y equals to a mass initially at k. And yeah, the second condition is similar, but just in the opposite direction. And we then define this Wasserstein distance between the mass distributions as the infimum among all this set of transfer plans times a cost function, which in this case is the graph distance between the nodes. So the graph distance between two nodes is just the length of the shortest path connecting them. And finally, we get that the curvature in function of this parameter alpha is 1 minus the Wasserstein distance divided between the distance divided by the distance between the nodes. So just to give you a quick example of how this will be computed in practice, if we want to compute the curvature of this edge x and y, setting alpha equals 0.2, we first define the mass distribution around x. So in this case, we put 0.2 mass at x and we equidistribute around the neighbors, and we do the same with the mass distribution around y. So as this is a tree and there's a unique path connecting two nodes, it's very easy to come up with the optimal transfer plan, which in this case, it just consists on moving all the mass to node x. And then we leave 0.227 mass in there, we move the rest to node y, we leave 0.2 mass in there, and we equidistribute around the remaining nodes. And we can easily get the value of the curvature in this way. So this construction may look a bit artificial at first sight, but it actually has quite a deep connection to the curvature in manifolds that I briefly explained at the start of the talk. So broadly speaking, both notions reflect the fact that when the curvature is positive, the average distance between respective points in small balls is smaller than the distance between centers, and the opposite when the curvature is negative. So in the continuous case, we have that these balls are small geodesic balls, and the distance between them is just the distance induced by the Riemannian metric of the manifold. And in the discrete case, we have that these balls are the massless distributions, and the distance between them is this Wasserstein's distance from optimal transport theory. And then we'll expect that graphs that have a more tree-like structure will be the ones with a more negative curvature. And this is because the mass distribution around adjacent nodes will not overlap as much. So we will need to move a lot of mass to go from one distribution to the other. And then we'll expect that graphs that have a more clear-like structure and that are highly connected will have a positive curvature for the similar reasons. So as you can see, this notion of curvature in a graph already gives us quite a lot of information about the underlying structure. And this has been used in different contexts. So for instance, it has been used to study the over-squashing effect that occurs in graph neural networks. So it has been found that edges with negative curvature are the ones with a higher, that impact more this bottleneck effect. So by identifying these negative curvature edges, we can try to find a better way for the information to flow to try to help this over-squashing. But it also has been applied to a lot of other contexts, for example, to study the stability of financial markets or to study the curvature of the internet to see how the information flows. So now we can also define an algorithm that uses these values of the curvature to try to find a set of edge weights that make the curvature of the graph constant. So this algorithm is called the Ollivier Ricci flow because it's kind of inspired on the Ricci flow on a manifold. So the Ricci flow on a manifold is just a process that deforms the Riemannian metric of the manifold to try to make it smoother. And kind of a similar thing will happen in this discrete case. So this algorithm can be divided in the following steps. So for every iteration, we want to compute the curvature of all the edges on the graph. So in this case, we will define the mass distribution in the following way, as it's shown in step 3. So this is the same mass distribution that I showed a few slides ago, but notice that now we have introduced this weight-dependent term and the mass distribution that is in function of a parameter p, which will just be a hyperparameter of the algorithm. But then we use this mass distribution to calculate the curvature of the edges using the same process that I explained. And then we update the weights of every edge using this iterative formula that is shown in step 5. So here, epsilon is just the learning rate, which in my project, we always set to 1. And then at the end of the iteration, we normalize the weight of the edges so that they don't expand to infinity. So this algorithm has some nice properties, especially to community detection problems. So I implemented it in a small social network and to illustrate some of its applications. So this is the Zachary Karate Club network, which is a very small social network that contains 2 social groups. So we would like to apply this algorithm to see if we're able to detect those 2 communities. So on those diagrams, you can see the curvature on the weights before and after applying the algorithm. And as you can see in the upper left diagram, the curvature of all the edges initially ranges from -2 to 1. And those are actually the lower and the upper bound of the curvature of any edge of any graph. And yeah, we can just prove these bounds using optimal transport theory. And then as you can see in the lower left diagram, the weight of all the edges is 1, because at the start, we're just working with an unweighted graph. Then after applying this Ollivier Ricci flow algorithm, you can see in the upper right diagram that the weights of all the edges has converged to 0. And that's why sometimes it's said that this algorithm flattens the curvature of the graph, even though the curvature doesn't always converge to 0, but yeah, in this case it did. And then in the lower right diagram, you can see that the weights have changed. So now if we look at the weights as a measure of distance between adjacent nodes, we will have that nodes that are connected by those purple edges will have gotten arbitrarily close together. And this is because the weight of these edges is close to 0, while they will have moved far apart from the nodes from this other group. So in this case, the algorithm has been able to fully detect the ground truth community structures that we had from our dataset. So I also implemented this algorithm in a slightly more complex network. So here you can see a graph network of 115 nodes, where every node represents an American football team. So 2 nodes are connected to each other if these teams have played at least 1 match against each other. So the teams are grouped into different conferences, which are represented by those colors in the right diagram. And we would like to apply the algorithm to see if we're able to detect those. So a very important factor when we're working with these community detection problems is a hyperparameter that's called the cutoff weight. And basically, what will happen is that when the weight of an edge has expanded above a certain threshold, we will consider that the nodes adjacent to it are far apart enough, and we will remove that edge from the graph. So then we will expect that at the end of the algorithm, we will get a set of disjoint graphs where every subgraph should represent a community.
I feel bag. It's Cheryl bag.
So this cutoff weight is actually the most important parameter. Is actually the most important parameter for the performance of the algorithm. So on those diagrams, you can see that if the cutoff weight is too small, then fewer edges than needed are removed. So you can see in this left diagram that we obtain fewer communities that we needed. So in this case, we only obtained 4 instead of 12. And you can see that different communities have been clustered to each other. And then if we set a cutoff weight, which is too high, the opposite will happen. So we will remove more edges than needed, and we will just get those isolated nodes that you see on the diagram on the right, which is not ideal either. So there's not like a standard way of finding the optimal value for this hyperparameter, but we can use the adjusted rand index, that is an index that compares the similarity between two clusters. So from this graph, you can see that the optimal value is achieved near 1.7. And if we use this number, you can see that the algorithm has been able to detect nearly fully the communities. There's only a few nodes that have been misclassified. So this algorithm is very computationally expensive because it has to calculate this cluster size distance for every edge and like every iteration. So for larger graphs, it's unfeasible. But for example, in this case, that it was a very small graph with a clear community structure, it managed to converge with just a few iterations. So even though this algorithm has been used in practice, and especially to investigate community detection, there's still no theoretical guarantees of its convergence. And this was the main focus of my dissertation. So when we started to look at this problem, and we realized that it was actually a very difficult problem because as the curvature depends on, is defined with this cluster size distance, and this distance doesn't have an explicit formula in general, it was very hard to work with this notion. And also, if you remember that we normalize the weights at the end of every iteration, this means that the curvature of an edge from one iteration to the other doesn't depend anymore only on the local structure, but will also depend on the global structure of the graph, which makes the problem also significantly harder. And finally, also as the weights are changing through the Ricci flow, it's very hard or impossible to keep track of the optimal path between two nodes because the optimal path will change as the weights change. So yeah, altogether, it turned out to be a very hard problem. So we focused on a simplified version of the algorithm. And in my dissertation, we were able to prove that this Ollivier Ricci flow applied to this graph G here on the right, and with this mass distribution only converges for alpha larger or equal than 1/3. So this mass distribution looks a bit strange, but it approximates the behavior of this other mass distribution that I showed here as p goes to infinity. So e to the minus x to the p, as p goes to infinity, gets steeper around x equal 1. And this is the behavior that we're approximating with this step function here. So the choice of this mass distribution made the problem significantly easier because it meant that we could express this Ollivier Ricci flow process as a system of piecewise linear maps where the parameter space could be divided into different regions. So that's what we did. So in case of the graph G, which is very small, we can divide the parameter space into just three regions. So we say that the weights belong to the first region when the weights of all the edges are the same, and this will be just in iteration 0. Then we say that the weights will be in the second region if the weight of the interior edge is smaller than the weight of the exterior edges. And yeah, also I should mention that because of the symmetry of the graph G, the curvature of the exterior edges will always be the same, between them. And then we say that the weights belong to the third region if the weight of the interior edge is larger than the weight of the exterior edges. So notice that when the weights belong to this third region, there's two possible optimal transfer plans between node 1 and node 3. So we can either go through the interior edge, which we will call path X, or we can go through the exterior edges. And that's why the region in this diagram on the right, the third region is subdivided into two subregions. So then the heuristics of the proof was to analyze how the weights transition from one region to another using linear algebra techniques. So specifically, what we did is to look at the eigenvector, to look at the direction of the eigenvector that is associated with the largest eigenvalue. And then we just looked at all the different cases. So with this analysis, we were able to find that when alpha is smaller than 1/3, we have that the weights bound between these two regions and don't converge, but they do when alpha is larger or equal than 1/3. We also obtained some results with experimental simulations that we did in Python. So here on the diagram on the left, you can see how the weights changes through every iteration of this algorithm. So the purple edges in this case, so the purple line is the exterior edges and the orange line, the interior edge. And you can see that the weights keep bouncing and don't converge. But then in the middle diagram, you can see that if we set alpha equal to 1/3, in this case, it indeed converges. And finally, in the 3D plot that I have on the right, you can see this change of behavior. So here you can see the different values of the idleness alpha through the Ricci flow and how the weight changes. So you can see that when alpha is 1/3, which is approximately like 0.3 something, there's like a change of behavior and the weights go from bouncing to converging. So in my dissertation, we only proved that the algorithm didn't converge for this small graph G, but we also found some larger graphs that had the same phenomenon. So here you can see some of the other graphs that we found experimentally that also had this bouncing of the edges. So broadly speaking, this phenomenon happens in graphs that are highly symmetrical. So they have these exterior and interior edges and have very small cycles, which in those cases are triangles. And those are the ones that create the bouncing. So I think an interesting question to investigate in a future project is if we can construct an arbitrarily large graph that exhibits this phenomenon, because in the project, those are the highest graphs, the larger graphs that we were able to find. And also an important thing to mention is that the whole proof is using this approximation of the mass distribution as p goes to infinity, which is not the one that is used in practice because this approximation will be very numerically unstable with the step function. And also in practice, we want to put more importance to the nodes that are connected by positive edges, but we don't want to completely disregard the nodes that are connected with negative edges, which is kind of what's happening when we're using this step function. But nevertheless, we were able to prove experimentally that when p is larger than 1/5, and p was this value for the smooth for the smooth mass distribution here. So when p is larger than 1/5, this mass distribution is similar enough to the mass step function that we're approximating, and the algorithm doesn't converge either. So I think, yeah, also another point that will be interesting in a future project will be to extend our proof to work as well in this smooth case that is used in practice. And finally, we also analyzed the robustness of both the Ollivier Ricci curvature and the Ollivier Ricci flow. So what we did for that is to generate a random graph and see how sensitive, and well, we generated a random graph and we calculated the values of the curvature of the edges and the weight of the edges after the Ricci flow. And we wanted to study how sensitive were those values to random noise. So for this, what we did is to divide the edges into two groups. So for the Ollivier Ricci curvature, we put all the edges that initially had a negative curvature in one group and all the others in another group. And for the Ollivier Ricci flow, we put all the edges that initially expanded in one group and the ones that shrunk in another group. So then our analysis was to see if the edges remained in the same group or they changed to the other group as we added random noise to the edges. So this accuracy score that you can see on the graphs is just measuring how many edges remain in the same group. So in the left diagram, you can see the robustness of the curvature. So as you can see, as the values of the standard deviation get higher, the accuracy drops to nearly 1/2, which makes sense because as there are only two groups for high values of random noise, the algorithm is basically guessing at random if that edge is positive or negative. And also we analyzed the confusion matrices, and we noticed that edges that originally had positive curvature were the ones that were more sensitive to noise. So I think for a future project, it would be interesting to see why those edges are less robust than the negative ones. But then what was also interesting is that when we looked at the robustness of the Ollivier Ricci flow, which is shown in the diagram on the right, this algorithm manages to recover the original weights of the graph. So you can see that even though the inputs of the Ollivier Ricci flow will be completely random for high values of standard deviation, the Ollivier Ricci flow manages to recover the original weights, which I think it's quite cool. But yeah, until here is my presentation. Thank you very much for listening. And yeah, let me know if you have any questions.
Thank you very much, Maria. That was fantastic. So we'll open it up now. If anybody would like to ask a question, you can switch your camera on and unmute yourself, and please feel free now to ask Maria a question. Are you able to unmute yourselves? Oh, Eric, yeah, would you like to ask a question? You're on mute, Eric. Oh, well, yeah, it looks like it might be muted. So instead, could you please put your questions in the chat and I can read out the questions? I think that we've got problems with the mics.
Stephen, Carl has a question.
Yeah. So yeah, go on, James.
Carl, you go first.
Thanks, James. Thank you so much for the talk, Maria. I was wondering, throughout your process, you presented analytic methods and you presented experimental methods and working with graphs and generating random data. While you were working through this, what was your process? Were you bouncing back and forth between analysis and generating random data and experimentation? Or did you kind of start with one and then move to the other?
Yeah, no, that's a very good question. I think the first few months we spent a lot of time doing simulations in Python just to get some intuition of how the algorithm worked and some of its properties. We experimented with different types of graph and understood why there was like this different behavior. And we actually first found this example of the algorithm that doesn't converge with experimental analysis and not the other way around. And then we come up with this proof to prove it theoretically. So I think, yeah, the experimental simulations were very important to get some intuition of what to expect along the algorithm.
Great, thank you so much.
Hey, James.
Thank you again, Maria, and congratulations on another prize that you've won. 2024 was a very good year for you. And 23 for that matter. So you mentioned that the algorithm was slow on large graphs. So do you think there's a way to speed it up?
I think so. The algorithm is very computationally expensive due to the Wasserstein distance, which is very difficult to compute, because to compute the Wasserstein distance, you need to find all the paths between all the nodes, and this for large graphs, it's really expensive. So I think if we use an approximation of the Wasserstein distance, maybe like a numerical approximation, it will already make the algorithm much more feasible.
Do you have any in mind?
I don't know any, but I think there should be, like, in optimal transport theory, some numerical approximation of the Wasserstein system.
Yeah.
Yeah, we didn't look at that.
Thank you very much.
Okay, Maria, I just have a quick question. Just to let the audience know, you are applying to do a PhD. Is that in pure mathematics? Is it related to graph theory? Is there any programming involved, or, do you have a PhD project in mind?
Yeah, so I would like to do a PhD kind of on this intersection. That was my dissertation. So I would like to work on the intersection of like topology, geometry, and machine learning. So that's kind of the projects that I'm applying for. So it's quite a new area that's called geometry deep learning.
That's fantastic. And so you're still programming on your new MSc?
Yeah, I'm taking a combination of computer science courses in active learning, and also like courses from the math department. So it's both like computational and theoretical.
Fantastic. That sounds really good. Does anybody else have a quick question? No. Okay. Thank you very much, Maria. I think we missed the beginning of the recording of the session, so I'm going to hand over to James now. But just for everybody on the audience, we will be running this competition every year, so please promote this to staff and students, and hopefully we'll make it a really successful event for the IMA. James, I'm now going to hand over to you, and you can introduce Will.
Sounds good to me. So good evening, everyone. Hope you're all having a nice time, and thank you for joining. So Will, if you want to start sharing your screen, I'll do a bit of a blurb. So as Stephen mentioned, this is something we run every year. And for those who maybe aren't aware of the competition and what it is that we did, this is running on the back of a competition that Stephen was running for the Northwest branch. And he thought at the for the 60th anniversary celebration, that's the 60th anniversary of the IMA, he would extend this out to the whole country. So what we ended up doing was asking universities across the country to submit essentially the top project for the student with the top project, and then they were all brought into a competition, and myself, Stephen, and a few other academics then rated and decided on like who would win, and the winner then gets to do this essentially. So Will came top. Maria came in second place. So without any more from me, I want to hand over to Will. So he's going to talk to us about the vibrations of an N-gon mass spring system and further geometry. So Will, please take it away.
Yeah, thank you for your introduction, James. So yeah, I'm Will. My talk's on vibrations of an N-gon. I won't say the title again because it's a bit lengthy. So this was my third year project, and Mum, you might want to mute yourself.
Sorry.
And this was basically a study of vibrational modes of discrete mass spring systems. So the first question you might be thinking is, well, okay, I'll start this again. So I've got an outline of the talk first. So part one, we'll look at these 2D N-gon systems. Part two, I'll move on to gyroscopic systems and how we can model the Coriolis force using this. And then part three will be on 3D systems. So the first question is, what are these vibrational modes and why are they significant? So yeah, a vibrational mode is pattern or shape something will vibrate in when it's excited at a certain frequency, and it'll normally be a combination of those. So on the left here, I have an example of when we look at the modes of vibration of a clamped string. So on the left is the lowest order mode, or the natural modes. It vibrates at the natural frequency, and we get the higher order modes here. So what you can think of this is actually a guitar string. So when you vibrate a guitar string, it'll end up being a combination of these with different amplitudes. And why are these modes significant? Well, here I have a clip of the Tacoma Narrows Bridge, and where one of its resonance modes was excited during a windstorm. So this is a torsional mode here, and we can see this twisting behavior going on. This bridge collapsed quite soon after, so for engineers, this is a really important problem to do, to look at the eigenfrequencies or eigenmodes. But this will look at that these resonant modes occur at. In my abstract, I mentioned tuning forks as well, and how modes are used here. So if you take a tuning fork, tap on the sides, it will vibrate at this fundamental mode. So here's an example: vibrates at 426 hertz. So you get a certain pitch, that you hear. Now, if you hit it a bit harder, you might excite a clang mode, which isn't as common. Sometimes you get this higher order mode also. Okay, so also, since we're talking about mass spring systems, I thought it's worth briefly recapping Hooke's law. So Hooke's law states that a force is proportional to a spring constant or spring stiffness times the displacement of the mass from equilibrium, and then we take a negative sign since it's a restoring force. Now, using Newton's second law, we rewrite this in this form, where F equals mass times acceleration, where the acceleration is the second time derivative of displacement. And we can make the substitution here that omega squared equals kappa over m, where kappa is this spring stiffness I've mentioned, and mass is a mass. So you might recognize this as the equation for a simple harmonic oscillator. And just to understand frequency a little bit better, I've got 3 examples here on the right where I've changed certain parameters. So first one, spring stiffness 1, mass 1, frequency 1. If we increase the spring stiffness here in example 2, the frequency increases and the spring or the mass oscillates faster. And for the final example, if the mass is 2, it oscillates slightly slower as the frequency decreases. So when we look at solving these problems later, the frequency will appear, and that's why I've introduced this here. So moving on to these 2D N-gon systems, which was the main topic. So to form the N-gon structure, we see here on the left. So on the left is a schematic of the structure. So the X and Y positions of these masses around what I'm going to call the rim of the N-gon. X equals r cosine 2 pi k over m, and Y equals r sine 2 pi k over m. So this is basically just taking discrete points around the circle. So here there's m masses shown. So yeah, k is 0 up to m minus 1, so m masses with an additional mass placed to the center of our coordinate axis, so 0, 0 of origin here. Now we connect these masses in the following way. So these black lines here are meant to denote these linear springs, and these are governed by Hooke's law. Now this looks much more complicated than the equation we saw before, but it basically just says the force from mass I to mass j equals, again, the spring stiffness, and this is from the spring stiffness of mass I off of a spring connecting mass I to mass j. EIJ is defined here as the equilibrium positions of the unit vectors from mass I to mass j in the equilibrium positions, and then this displacement here is the displacement of mass I, displacement of mass j. So we can find the governing equations for this system by looking at the 2 cases. So either we're the central mass, so we're connected to all these masses on the rim. So the force from central mass to one of the cape masses equals mc uc, where the c subscript basically just denotes the central mass, and we sum all these forces up. Or we're a mass on the rim, so we're connected to central mass, mass up, head, or mass behind. So this is behind, head, center, and now we have k equals 0 up to m minus 1 mod m. So this mod m just makes these, basically connects it as a circle, because otherwise we'd have a -1 and something would happen. So to find the eigenfrequencies and eigenmodes of these systems, these vibrational modes I mentioned, we make an assumption that the motion is periodic or time harmonic. So I'll first assign the x components of displacement to xi and the y components to eta. I'll arrange these in a vector that I'll call q here. So these are all the x components and the y components, and this is a column vector, hence this transpose. And then we make this time harmonic assumption. So it's basically saying the x and y components of displacement of point masses is equal to the real part of an amplitude multiplied by a periodic function e to the I omega t, which is defined below, where omega is the radiant frequency I mentioned before. Now in the next slides, I'll drop this real part. So to find these forces and to solve this problem, we need a stiffness matrix. Now, in this black box here is just what we had before with the addition of this q double dot p. It just has a minus omega squared pop out. So this is the second time derivative of qp. And we can actually write these equations of motion as a linear system now. So m q double dot p equals kq, where m is this mass matrix defined, well, it's a diagonal matrix with all the point masses. So it's repeated twice. We have the x components of the masses for the x part, and then the y part are the same, but it's repeated twice since we have x and y. And we can think of this equation here basically as Newton's second law. So ma, you can think of this as the acceleration, equals kq, where k is the stiffness matrix I just mentioned. So this k basically denotes all the force interactions that are going on in this system. And making the substitution of q and q double dot, and we get this minus omega squared that pops out, and I've also labeled this a here, where a is our amplitude, as I mentioned before. We can rearrange this to just look like an eigenvalue problem. Now, if we require the matrix in brackets to be degenerate, we'll get a set of eigenfrequencies and a corresponding set of eigenmodes. And we can plot these modes. So I ran some simulations in MATLAB. So for modes for 40-gon, we get 4 categories. 4 main categories. So we get rigid body, translations, and rotations. and these correspond to 0 eigenfrequency. We get purely radial modes, so we have kind of this star shape in this breathing mode here. We get some tangential modes that are only really moving around the rim of our N-gon, and mixed modes, which are a combination of tangential and radial modes. So yeah, I think these are some quite nice animations. So next I thought, what would happen if we included concentric N-gons? So basically adding more. Now this diagram looks a bit more complicated, but we basically just added more N-gons. The equations for the x and y positions now have this RL, where this R will be a vector of radii that's gradually increasing. And yeah, so this system becomes slightly more complicated. So this is the only bit of code, by the way. I used object-oriented programming to do this. So this is my class to define a mass object, and it will have a mass value. It's what it's connected to, and it's x and y position. So we can just create an array of these mass objects, iterate through it, and this will just create our stiffness matrix for us. Now you'll notice these superscripts up here as well. And in the next slides, I'll just mention these. So for the governing equations of the system, they're tweaked ever so slightly. So for the central mass here, we now have this 0, 1, and this denotes the central mass is lying on rim 0. I'll alternate between N-gon and rim, and it's connecting to rim 1. So apart from that, it's the same as before. For the innermost N-gon that's lying on these ones lying on rim 1, we have these equations, intermediate N-gons, these ones, and outermost N-gons, these. So outermost would be one of these if we didn't have this. So this is like the cutoff one, and we can see these k plus 1s from before, but also the addition of like p plus 1 and p minus 1 to denote rim before or rim after. Now I've set L to be greater than 2, where L is the number of N-gons, since if L equals 2, we have this kind of degenerate case where we lose this equation here, since we only have this rim and this rim, so we don't need this extra one. So again, we can set this up in the same way, find a stiffness matrix, set up a mass matrix, solve an eigenvalue problem, and we can look at some modes. So first I have the modes for the N-gon with 2 rims. These are just a few examples. There's many, many more to choose from. So we kind of have these radial modes again, these rigid body translations and rotations. So these kind of resemble what we've already seen. And for one more example, here's the 6-gon with 4 rims. I think this looks kind of like a spider web, and this one almost looks 3-dimensional. We have this breathing mode again. I think these are quite nice. So it's also worth mentioning I put together a MATLAB app that basically meant you can put like discrete points on, and it'll create these N-gon systems for you and solve this eigenvalue problem, and you can get all these animations out. But so to move on to part 2 of the talk, I want to talk about what Coriolis force. So this is a force introduced into rotating systems, and we can actually use gyroscopes to model this. So Coriolis force is traditionally defined with this equation. So minus 2m the acceleration, so the second time derivative of the displacement, or the first time derivative of displacement, cross product with an axis of the axis we rotate around. So you can derive this equation from looking at the sound equation of motion in a rotating reference frame, rotating around axis omega. Now I'm going to define my gyroscopic, or my equation for these gyroscopes, with this parameter alpha. So this will be our gyricity parameter, or strength of gyroscopic force. I'm going to take my axis omega to be the z-axis. And what this does is introduce some coupling between the x and y components. So x is now coupled to y is now coupled to x. And since we're taking z to be our axis of rotation, there's no coupling to z. And this animation here, I've solved these equations for a point mass, and we can see what's actually going on. So here the velocity is this blue vector, this green is our axis of rotation, or the z-axis, and then this red arrow is the force. So basically by taking the cross products, we get a force that's acting orthogonal to the velocity and this axis of rotation. And hopefully you can see here how it imitates this rotation. So we're rotating around this main axis. So if we now incorporate these, basically bring these equations together, so we have our Hooke's law from before and our gyroscopic force, and make this time harmonic assumption for the gyro equations, we'll just have a I omega alpha pop out, and this U now contains x, y, and z components of the displacement. And I can again bring these together into our matrix form I mentioned before. So minus omega squared ma equals ka. plus I may get alpha C, where C we can call kind of a coupling matrix, Coriolis matrix, or kind of gyro matrix, how we want to name it. And we make this assumption that our parameter alpha depends on the frequency and this extra parameter. So this is called assuming it's an active system. Basically means the gyricity depends on the frequency the system is vibrating at. And this just means we can, again, set this up as an eigenvalue problem. So now we'll have this matrix here, and this will be a Hermitian matrix, so we'll still get real eigenvalues. And again, we can solve these equations and get a set of eigenmodes and eigenfrequency. So I wanted to compare some trajectories to what we saw before so we can really see what these gyroscopes are doing. So this is that pentagonal shape I mentioned before, and we can see they normally just have these straight line trajectories, but by adding gyroscopes, we get these elliptical orbits that you'd probably expect to see. And for one more example, we have this one. This was kind of the closest one I could find to resemble it. And we have, again, these elliptical trajectories. So rather than just moving back and forth, we have this rotation going on. And there's one more example I wanted to mention that I think is quite nice of these gyro examples. And so this is a weirdly specific one where we take a triangular lattice. So this is basically the concentric n-gons. For each layer, we rotate a little bit. So we set up these triangles, connect them in the way you can see here. And I've taken the radial springs to be weak. They get gradually less stiff as we move away from a center. The gyricity, or this gyroscopic force, increases as we move further out. And we have this heavy central line. So it's a weirdly specific example, but yeah, and we basically see these like polygon shapes rotate around. So if you focus on one point, you can see kind of the square rotating around or a pentagon rotating around here. It's a good time to reference a paper that did kind of a similar experiment, but they took a cylinder filled with some fluid and rotated it, and they got some similar polygon shapes. So we can see these kind of like stable states that rotating systems like to end up in. So that finishes the gyroscope part. But if we bring what we've talked about together, so look at gyroscopes on three-dimensional systems, I'll consider one example here. So we can look at the icosahedron. So icosahedron in black, I've added a central core and then connected the springs in red, as we can see. And we can look at some of the modes for these again. By solving the equations, I've taken the gyricity parameter, so this beta, to be 0.8 here. So the gyroscopes are quite strong, and everything else is taken to be 1. So mass is 1, stiffness is 1. And sorry for these slightly awkward axes showing it. It's quite hard to record 3D animations using MATLAB, but we can see these rigid body translations and rotations from before, except we're getting more, rotation going on. And we can see this mode here. So this is a zero frequency mode. And this is mode 7, so the first non-zero eigenfrequency modes. And we can look at the next mode here, and we get some quite interesting rotational behavior. Yeah, this is quite hard to see. So I do have some trajectories we can look at. And I'm going to have to jump out to MATLAB for this, and I'll just play around with it because we get some quite interesting symmetries that appear. So I mentioned symmetries, but we don't really get symmetries for the first mode, which is the rigid body translation. So this is just mode 1, and we can see these nice elliptical orbits. And if we look at mode 7, so the next mode I mentioned, so this is the first non-zero eigenfrequency. So when we don't get these rigid body translations, we get these symmetries up here. And these are the trajectories of the animations we just saw. So I think they're worth playing around with because I think they're quite pretty, the patterns that come out. So I'll look at one more. So this was mode 8, so the other animation we looked at. And we get this almost complete circle filled in if we look from above, which I think is quite nice. And yeah, we can look at all these. So I'll just jump back to PowerPoint now. So finally, I mentioned a geophysical link in my abstract. So there's a structure I'm currently looking at and working on at the moment. So this we can think of as a continuum model of this structure. So this is basically a sphere in the middle encased in a shell, encased in another shell. Now, this is already quite a complicated problem to write the equations of motion for if all of these have different elastic properties. So you would already consider considering a discrete model of this. And to add this rotational behavior, so this Coriolis force, is even more complicated. But as hopefully you've seen, using gyroscopes makes it really simple. And yeah, so the geophysical link is, you might look at this and either think, what the hell is that? Maybe it's a dartboard. Maybe it's the structure of the Earth. We can think of this white core, white sphere here as maybe the inner and outer core. This red shell here is maybe the lower and upper mantle. And then this blue shell on the outside is maybe the crust of the Earth. Now, you might say, okay, what are you on about? This is crazy. And maybe it is a little bit, but it's just a way to model rotation and maybe look at some vibrations of the Earth. And obviously eigenmodes, like I mentioned before, the guitar string, are just well, you combine all these eigenmodes to look at a true vibration of something. But this is, a nice model to look at that. Yeah, I'm currently studying. And yeah, so hopefully you've enjoyed those animations. This is kind of my wrap-up slide. So I try to build on quite gradually, and this is how I, worked on this project. So yeah, started with a simple N-gon system, looked at this more complicated one. The code got more complicated, then eventually culminated in these 3D systems. And you might also think, what's the point in looking at these kind of structures? Well, there's these materials called metamaterials, and they have these unique properties. So these are man-made materials with, certain properties. So they might be used to create waveguides, and so to guide certain waves in certain directions. So say in optical fibers, these might be used. So, you sent a wave down an optical fiber, you want it to go in a certain direction, you don't want to lose it. And you can create these kind of gyroscopic systems or these chiral systems to imitate this, or create these materials that have this certain behavior. So that's my talk. Thank you for listening, and thank you all for coming.
Thank you very much, Will. Where's the clap? There's the clap. Okay.
Oh, thank you.
So we've got 10 minutes or so. Does anyone have any questions for Will, including Will's family? You can jump in and ask questions if you feel like you can. Nathan, go ahead.
I'll try my best.
Hi, I work in noise and vibration, so this is very interesting. I was wondering, firstly, is your MATLAB app that you mentioned available somewhere online, and can you share a link to it? That would be really good.
I don't have it available online, but I can share details with you, and we can talk about that.
Cool, thanks. And my other question was around your relation that you shared, that you assumed between, I think it was between the frequency and the Coriolis force. You had a
yes, let me jump back here. So this is this one. So it's assuming the system's active.
Yeah. So what I was wondering is that a sort of physical assumption, or is that something to kind of simplify the problem?
So it does simplify the problem, but you do also, it basically turns it from like a transient problem into an eigenvalue problem. Yeah. But the transient problem will still contain elements of the eigenvalue problem. If that makes sense. So if you solve this eigenvalue problem, and you basically use it as the building blocks for the eigenvalue of the transient problem you'll look at. But it is a bit of a simplification, but it is still very valid and worth looking at, and it will help you piece things together a bit better.
That's great, thank you.
Thank you for the question.
Thanks, Nathan. Following up with that, what are some other assumptions you could make for this alpha then, rather than it be based on frequency? What else might you choose?
Well, choosing this is all you really need, because you want it to be set up as an eigenvalue problem, which simplifies the system a lot, and you can end up with this Hermitian matrix. So you probably don't need to assume too much more than that. Otherwise, you'll be looking at the transient problem, which is a slightly different one to what I've looked at here.
Makes sense to me. And if anyone else has any questions, then feel free to jump in. Go ahead.
Hey, James, I'll just ask a similar question asked Maria. Will, you're applying to do a PhD at Imperial. Is it related to this work, and you think you'll continue your work with MATLAB? Are you using MATLAB now in your MSc course?
Yes, so this was all with MATLAB. It's related in a way that it's all waves. So this is mainly standing waves, and these eigenmodes. I'm actually looking at some work now, looking at periodic waves, and yeah, creating these like periodic waveguides.
So is there this PhD you're applying for at Imperial? Is there a title for the research?
So it is time explicit finite elements methods for multi-scale and multi-physics systems, from like simulating ultrasound waves on the GPU. So it'll be coding in CUDA. So that's the Orion code for NVIDIA GPUs. And basically setting up finite element methods that they can, well, use less assumptions than what's available at the moment. Because a lot of calculations will be done with CPUs. And well, they're slow. So using GPUs means we don't need to take so many assumptions into account.
And have you heard of TPUs? You know, with a Google Colab, you can use tensor processing units.
I have heard of it, but I haven't looked into it at all.
You can look into that later. Okay, thank you, James. Anyone else have any questions?
Whoa, could I ask a quick? Oh, thanks for the talk, by the way. Really, really interesting. Could you just go to the slide where you had the shape appearing in the fluid? I'd just like to look at because it just reminds me. I don't know if the same phenomenon is happening. Is that did you say it's in a cylinder?
Yeah, so this paper I've referenced here is in a cylinder. So they took a cylinder of fluids and then rotated the cylinder, and these polygon shapes appeared.
Okay. It just reminded me there's a shape on the North Pole of Saturn.
Yes.
The planet. Is that the same? I assume that's the same phenomenon
Yeah, so that was using gyroscopes as well. So one of my supervisors actually wrote that paper, and I'm working with a PhD student that submitted that now. So similar, yes, but obviously very different systems. But
yes.
Yeah, so that was looking at so they took a gyro pendulum, so a pendulum with a gyroscope attached, and looked at its kind of some of its stable states that it like to be in. So some of its like cycles it ended up in, and some of them were these polygon shapes.
Great.
Kind of answers it.
Thank you.
I hope I tried.
Thanks, Jack. Kyle, you're probably the last question.
Thanks so much for the talk. Well, I really enjoyed it, and I enjoyed the animation and seeing how the normal modes were emerging. You mentioned the significance of avoiding those normal modes when you showed the wobbling bridge. Do your methods yield any novel ways of making recommendations to prevent normal modes, or is this just a pure exploration of how these modes arise?
So yeah, most of this work was my third year project, which was just purely kind of an academic toy problem. So this N-gon, simple systems. But yeah, what I'm working on now, there will be some sort of insight. So we'll be using gyroscopes to kind of create stop bands and stop some waves propagating through certain parts, and where you can choose path bands. So you can, are you familiar with dispersion curves and these kind of things? Okay.
No, it's not my field, unfortunately.
Okay, well, when you have waves propagating through some structures, you have these curves, and you can use gyroscopes to raise or lower the frequencies these waves will propagate at. So you can maybe create some systems that will change how these waves propagate. So and create some damping and stop these. So you can have sensors that detect how fast these gyroscopes should spin up. Might be able to stop these resonance frequencies occurring.
Okay, great. Can I sneak in one very short, fun question? I listened, if that's allowed. I listened to an interview with Roger Penrose, and he said that mathematicians would describe him as a physicist, and physicists would describe him as a mathematician. And it feels like you're playing in the area where you could fall into the similar. So I was just wondering, if you arrive at a party with mathematicians and physicists, which group do you gravitate towards?
So yeah, my degree is applied
There's
maths.
a correct answer and an incorrect answer, may I add? Think
Yeah,
about
we
where
are
you're
with the IMA right now. So yeah, my degree
You
is
can also
applied
disregard
maths.
the question.
I'd probably put myself in the mathematician side because, well, most of these problems are eigenvalue problems, and mathematicians love eigenvalues. So, and I love my eigenvalues now. When I first saw them, I thought, what the hell are these? But now I can't. I see them everywhere. So I'd put myself in the mathematician side, definitely. But it's interesting to see the physics applications, definitely.
Very good. And a correct answer, I think. So I think we're up now. I think that's the hour. So I would like to thank Will and Maria again for their time and putting in a lot of effort into these projects and presentations. And, we should all wish them the best of luck for the future. And I'm sure this is not the last time we've seen Will and Maria in these quarters. So look forward to whatever you're doing in the future.
Thank you.
Thanks, everyone.
Thank you, James. And Merry Christmas, everyone, and a peaceful and prosperous new year. And we'll see you all in 2025. Okay. Bye, everybody.
Bye.
Thanks, folks.
Bye.